In this video, we're going to look at solving systems of initial value problems using both the explicit Euler method and using the classical Runge-Kutta method that we studied in the previous lectures. So, a system of initial value problems is usually given as follows. There are let's say n functions, function x1, function x2, all the way up to x sub n. These functions are dependent on the time t. What we know, or what's given, are the rates of these functions with respect to time. They're given as different, they're given in different forms, different functions. And knowing these rates and knowing the initial values at a particular time point for the functions x1, x2, and so on up to xn, we'd like to know how these functions evolve in time as time progresses. So basically, what we're trying to find, given t0 and given the values of x1, x2, x3, and xn at the time t0, so we know these values. Here we're using the subscript to indicate which function, so x1, x2 up to xn, these are the different functions, and the superscript indicates which time point. So x sub 1 is the first function, superscript I plus 1 is at time t sub I plus 1. Is equal to x sub 1, which is the first function, at time ti, plus a slope multiplied by h, where h is equal to the difference in the time, ti plus 1 minus ti. So each of these functions are equal to their initial values plus the relative slopes multiplied by h. So again, these are the slopes. These are the equations where to find x sub, the x1, x2, and so on up to xn. The question is, what do we use for the slopes? If we use the explicit Euler method, we evaluate these slopes at the initial time points. So the first slope, phi sub 1, is equal to f1 evaluated at the values of these functions given at time point t sub I. Phi 2 is the value of the function f2, which is the slope f2 evaluated at the initial point. If we use the Runge-Kutta method, the classical Runge-Kutta method, then these slopes, phi 1, phi 2, and so on up to phi n, are, as we mentioned before, they are a weighted average of this other slopes. So phi sub 1, which is the first slope here, is 1 over 6 multiplied by the slopes at different points. K subscript 1, 1, 2k subscript 1, 2, 2k subscript 1, 3, and k subscript 1, 4. The first, the one appearing in the subscript indicates the first slope, and 1, 2, and 3, and 4 are the slopes at different points. Similarly, phi sub 2 is equal to 1 over 6 multiplied by 4 different slopes. The 2 in the subscript denotes that we're evaluating phi 2, which appears in the second equation. 1, 2, and 3, and 4 are different points within the domain between t sub I and t sub I plus 1. So we're going to utilize this method to solve an example. Utilize the two methods, the explicit Euler method and the classical Runge-Kutta method, to solve a system of differential equations, of initial value problems. So as an example, a system of the differential equations can arise when we have a second order initial value problem. So for example, if I have the let's say x is a position, let's say I have the acceleration of of a particle given by a certain function. So I have the second derivative of x with respect to t squared given as a function, with two initial conditions for the position x and the velocity x dot or x prime dx by dt. If I know the initial velocity and the initial position, I will be able to solve this initial value problem, but I have to divide it into a system of two differential equations. First, we set the velocity as y, so assuming that x is the position, dx by dt is equal to y, and then the acceleration is the rate of change of the velocity, dy by dt is equal to f x and t. So now we have a system of differential equations with two unknown functions. The first function is x and the second function is y, and we have two different slopes. In the very first lecture, when we talked about introduction to ordinary differential equations, we presented an example in which, or we presented the equation of a system that is damped, where the acceleration is given as mg minus kx minus a coefficient multiplied by the velocity of the particle. And so we're going to solve this system using using the numerical method, one of the two numerical methods that we are talking about in this lecture. Just remember that the exact solution is given for the position and for the velocity as follows. So this equation can be solved using the dsolve function in Mathematica, and you have the code online if you'd like to try it out. This gives me this equation gives me the position as a function of time, and this gives me the velocity as a function of time. The parameters of the problem are at the beginning of the simulation, or at the beginning of the time, when time is equal to 0, the position is 0 and the velocity is 0. The time goes from 0 to 2 pi, and h that we're going to use for the two methods, the explicit Euler method and the Runge-Kutta method, h that we're going to use is equal to 0.1. The time increment is 0.1. So we're going to start at time is equal to 0, then 0.1, 0.2, 0.3, and so on, all the way up to 2 pi. All right, so the numerical solution, as we mentioned, we're going to convert them into two differential equations. Initial value problems. The first one sets dx by dt is equal to y, and dy by dt is equal to 10 minus x minus 0.15y, where y is the velocity. Dx by dt is the velocity, and dy by dt is the acceleration, is equal to this equation. This is an initial value problem, which means I know I should have values for x and y at the beginning at time equals 0. And they're given that x prime, or dx by dt, which is y at the time equal to 0, and the position at time equal to 0, they're both equal to 0. We're going to use time as starting at 0, 0.1, 0.2, and so on up to 6.3, because to reach 6.3 is roughly equal to 2 pi. As time evolves, we're going to have corresponding position and corresponding velocities. The positions will be denoted x0, x1, x2, x, and so on up to x63, and the positions will be denoted, the velocities will be denoted y0, y1, y2, and so on up to y63. So x1 and y1 represent the position and the velocity at time t1, and x63, y63 correspond to the position and the velocity at time t sub 63. Using the explicit Euler method, x sub I plus 1 is equal to xi plus h multiplied by the slope of x. Y sub I plus 1 is equal to y sub I plus h multiplied by the slope of y, and these slopes are evaluated at the initial point. X sub I, y sub I, t sub I. X sub I, y sub I, t sub I. Alright, so x sub I plus 1 is equal to xi plus h multiplied by dx by dt. Dx by dt is given as y. And dy by dt, which is given here. And don't forget, I'm going to write it for you here to remember that dx by dt is y, and we have, and this is equal to dy by dt, and we also have dx by dt is equal to y. So this is the slope for x, and this is the slope for y. All right, so we have the initial values, and when the time is 0, x sub 0 is equal to 0, y sub 0 is equal to 0, so we can calculate x1 and y1. x1 is equal to x0 plus h y naught. x0 is 0, y0 is 0, and x1 is 0, which means that this numerical method predicts that after the time evolves to 0.1 second, the position has not changed, it stays at 0, but the velocity has changed because there is an acceleration, and so because of acceleration the velocity has changed. Y1 is equal to y0 plus h multiplied by the acceleration, and the acceleration is given by this value, 10 minus x minus 0.15 y, 10 minus x0 minus 0.15 y0. x0 and y0 we're going to use at the beginning of the increment, which will be equal to 1. So when at t equal to 0.1, this is the value of x1, this is the value of y1. As we proceed, we can get x2 and y2. x2 is equal to x1 plus h y1 from this equation. y2 is equal to y1 plus h multiplied by the acceleration from this equation. We know x1, we know y1, which are the x1 is 0, y1 is 1. H is equal to the time increment, which is 0.1, so I can calculate x2. Similarly, I can calculate y2 at 1.985 and so on. So then I can use x2, y2 to calculate x3, y3 and so on. Because we know the exact solution, I can look at how the numerical method compares to the exact solution when I plot the exact solution, which is the blue curve, versus the numerical solution obtained by the black dots. You can see that maybe at the beginning the position and the velocity are accurate, but the accuracy is lost as we evolve in time. As expected, the error accumulates in these methods because every small increment has a small error. The error, as time goes by, this error accumulates, and the black curves or the black dots deviate more from the actual or the exact solution given by the blue curve. So we're going to repeat the same example, but instead of using the explicit Euler method, we're going to use the classical Runge-Kutta method. So again, writing the two equations here, dx by dt is given as y, which is the position, the first slope of position is the velocity, and the velocity, the rate of change of velocity, is the acceleration. It's given by this 10 minus x minus 0.15 y. The Runge-Kutta method states the new value of x at time t sub I plus 1 is equal to the initial value of x sub I, the initial value for x, which is x sub I, plus h over 6 multiplied by these slopes, k11, k12, k13, k14, which are slopes evaluated at certain points within the time interval. Similarly, the velocity y sub I plus 1 is equal to y sub I plus h over 6 multiplied by these slopes. And these slopes are the slope of y, which is f2, 10 minus x minus 0.15 y, but evaluated at specific time points within the interval. Lots of computations, but you will see that with these computations, the method will prove to be very, very accurate. K11 is the slope of dx by dt evaluated at the initial time point. So the initial time point is, so dx by dt is given as y, and so it's y sub I evaluated at the first point. The k sub k to 1, which is this, it's given as the slope f2, which is the slope of y, it's dy by dt. As you can see, the expression contains x and y and could contain t as well. Which values of x and y and t? It's the initial values, x sub I, y I, and t sub I, and therefore it's 10 minus x sub I minus 0.15 y I. So this is the value of k21, and this is the value of k11. k12 is given as the slope evaluated at this x, this y, and this t. This x is equal to x sub I plus h over 2 multiplied by k11. And here's the value of k11. yi is equal to, or the value of y is equal to yi plus h over 2 k sub 21. And this is the value of k21. And ti plus h over 2, this is the value of the time in that is at which this slope is calculated. When we substitute these in the equation of f1, we'll get yi plus h over 2 k21, because really f1 is nothing but y, and so this is the value of y that I need, and this value of y is y sub I plus h over 2 k21, y over I plus h over 2 k21, where we already have a value for k21. k22 is basically this slope. It's the slope of y, f2, slope of y, evaluated at this value for x, this value for y, and this value for t. When we substitute this value for x, this value of y, and this value for t in the expression for dy by dt, we're going to get this expression. And so on and so forth, we can find the values for these different slopes. Again, lots of computations, but let's see how this is calculated. You can try this by hand, substitute the different values, and you can usually the best way to do this, the best method is to use Excel. It's really straightforward to use Excel and calculate these different k's and the corresponding x1 and y1 as time evolves. I would recommend that you try this method by hand so that you can see how these calculations are done. I'm just going to skip through these calculations and then show you the final graph after the values are found. You can see that this method is very, very accurate even after a long period of time. So after a period of 2 pi, you can see that the black dots, which is the numerical solution, is very close to the exact solution. This method, as we mentioned, is the error is directly proportional to h bar 4. So when we're using a small h, there is really very small error associated with this method, and the method is very able to capture the response numerically even at a large time for a large period of time. When we compare this method with the explicit Euler method, you have a tool online. You can change h and see how the solution is affected. Obviously, with the explicit Euler method, especially when there is high changes in slope, the method is losing accuracy. The classical Runge-Kutta method, for the same h, it still is very good in predicting the behavior as time evolves. Obviously, it is much easier to predict. It is much more accurate, but it comes with lots of computations, as you saw.